Hi, welcome to Sam's Maths Adventures. This is episode 4, how to differentiate e to the x, but probably not the way you've sort of seen it before. Um, so let's sort of start off with, uh, the way it was introduced to me when I was at school was we were just told that, e to the x has this great property where the derivative of e to the x is e to the x. Now, that doesn't feel very satisfactory. It's just sort of telling us that fact. So there are sort of slightly better ways you can do it. So one of those ways is that you can define uh, in sort of two different ways that this is generally done. Either e to the x is given by 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on and so on. Or the other way it's done is sometimes it's defined as e to the x is the limit as n goes to infinity of this sort of expression 1 plus x over n to the power of n. And these are sort of ways in which e to the x is kind of defined, and we're sort of told that e is this irrational number, 2.718281828, and then something else. It doesn't repeat 1828. Something like this. Now, this always kind of struck me as a bit unsatisfactory because any of these results, if you differentiate either of these, you are going to find that you get the sort of expected property that the derivative is itself. But why are they e to the x? It seems a bit strange that this is the definition we give. So that's sort of something I've been working on for sort of a few years in the back of my mind now. And I've finally sort of put it all together in a way that's sort of reasonable. So this is how we should really differentiate e to the x. So the first thing we need is we need a sort of proper definition of a to the power of x, where a is any number greater than 0. Okay, that's sort of where we're going to start, because this sort of is a bit weird because x is any real number here. So we kind of are told that it's defined by this sort of sequence idea of, well, a to the n we know is just a times a times a times a n times, and then that's integers done, and then a to the p over q for some rational number is the qth root of a to the p. Okay, that's fine. But then a to the, let's say, what is a to the pi? That's then a bit wishy-washy. So we're going to start by doing that properly and sort of rigorously. So I'm going to say that a to the x is equal to fa of x is the unique function, unique continuous real valued function such that, so fa is going to go from real numbers to real numbers, such that the sort of two properties we need are property 1 is that fa x plus y is fa of x times fa of y. Okay, this is sort of one of our laws of exponential, that sort of a to the x plus y is a to the x times a to the y. That's sort of fine. That's a normal property. And then we also want the property that fa of 1, which is a to the 1, must equal a. Okay, that's a reasonable property. And so my claim is that there is nothing else that sort of satisfies these properties other than a to the x. And so we can sort of construct a to the x using these rules. So first thing that we should note is that fa of x is fa of x plus 0 is fa of x times fa of 0, and so therefore fa of 0 is 1. And that agrees with what we would normally say about a to the power of 0 is always going to be equal to 1. So that's a good start. And then sort of we can also say fa of 0 is fa of x minus x is fa of x times fa of minus x, but also this is equal to 1, right? That's what fa of 0 is. And so therefore fa negative x is 1 over fa of x. That's sort of our next standard rule of exponentials, and our fa satisfies that, so that's good. And sort of the last one here is that a to the p is fa of p is fa of sort of where p is an integer and q here is going to be some integer that is not 0. Maybe I should have called this z star. So fa q times p over q, and so this is fa p over q to the power of q, right, just from our sort of recursive properties, or what that's really saying is that fa p over q is the qth root of a to the p. So that's another sort of property of exponentials, and that's fine. And sort of note that we sort of always have to take the positive root, because for most rational numbers, there is no negative root to this equation, right? Obviously, if q is a multiple of 2, then it's fine, but q is not always a multiple of 2. Okay, so we just always take the positive root for continuity reasons. Otherwise, our function is going to sort of jump around as x varies. Okay, so I sort of prove this by several theorems, which are a bit sort of monotonous and not very exciting. So what I will do is I'm going to put my sort of proper notes for this, where I sort of prove everything rigorously. I'm going to put them on my website, put a link in the description of this video. So for this video, I'm just going to sort of give you the outline and the general vibe. So this function fa, when we sort of restrict it to q as we defined it, right? So far our fa is only really defined on q, is continuous at x equals 0 from above. So it's sort of a very sort of loose property of, we're not saying it's continuous everywhere, we're not even saying it's continuous at 0, we're just saying that, and also for a greater than 1. We're going to generalize to anything greater than 0 later, but for now a is greater than 1. So what we're saying is that whenever a is greater than 1, and if epsilon is greater than 0, then there exists some d0 epsilon, so that for every rational number, if 0 is less than or equal to p over q is less than d0 epsilon, then a to the p over q minus 1, because this is a to the 0, this is going to be less than epsilon. So it's sort of like continuity, but only for one side. We're not even going to worry about the other side of 0. And the way I sort of proved this is using the AM-GM inequality. So if we have numbers x1 to xn, which are all sort of real and greater than or equal to 0, their arithmetic mean the arithmetic mean is sort of the usual mean. Okay, so the arithmetic mean of these is 1 over n times the sum from I equals 1 to n of xi. And their geometric mean is kind of like the mean, but you replace addition with multiplication. So it's the sort of nth root of the product from I equals 1 to n of the xi. And what the sort of theorem we're going to use is that the geometric mean is always less than or equal to the arithmetic mean. And the reason for that is that the geometric mean is sort of logarithmic. Okay, so it's kind of the log of the geometric mean is the arithmetic mean of the logs of our initial things. So what does that mean? Well, the bigger the number is, the less changing it is going to affect its log, right? Because log sort of looks like this, and so big changes can mean quite small changes in logs. And so the larger numbers are sort of much more relevant to bringing up the arithmetic mean than they are to bringing up the geometric mean. That's not a rigorous proof, but that's sort of not what we're here to do. And so that means that if 0 is less than, or less, and we'll say P over Q is less than or equal to 1, so Q is greater than or equal to P, we're going to sort of assume that P and Q are both positive here. Then what that means is that 1 plus B, where B is sort of any number we want to the power of P over Q, this is the geometric mean of 1 through this sort of Q minus P times, and then 1 plus B repeated P times, right? Because we sort of multiply all of these together, we're going to get 1 plus B to the power of P times 1 to the power of Q minus P, so 1 plus B to the power of P, and then we take the Qth root of this. So that means that it's less than or equal to the arithmetic mean of the same numbers, which is going to be equal to, well, we add them all up, we're going to get 1 plus PB plus Q, right? Because we get Q minus P plus PB divided by Q, which is 1 plus P over Q B, and so we get this sort of inequality using the arithmetic geometric mean inequality, so P over Q less than or equal to 1 plus P over Q B. And that sort of tells us that we can sort of cause this convergence, because we say, well, if we let this thing be equal to A, then A to the P over Q for P over Q less than 1, remember, is less than or equal to 1 plus P over Q A minus 1, and so we can sort of make this as tight to 1 as possible by just sort of making P over Q smaller. And so that's how we prove that this sort of D0 epsilon exists. And we can just call it a half epsilon over A minus 1. And that sort of gets rid of this equal to by adding in an extra half. Apart from when A is equal to 1, but we're sort of saying A is greater than 1. Okay, and then this actually tells us that FA is continuous from both sides at 0. And the way we do that is we sort of use the fact that 1 over x is continuous at 1, right? So for all epsilon greater than 0, there exists some phi epsilon greater than 0, such that mod of x minus 1 is less than phi epsilon, then mod of 1 over x minus 1 is less than epsilon, right? So continuity, but sort of for 1 over x now. And then we sort of say that, well, because we know that a to the negative p over q is 1 over a to the p over q, we can kind of use this continuity on both sides to sort of bring our continuity from above into continuity from below. So we sort of say if x is mod of x is less than the minimum of d0 epsilon and d0 phi epsilon, like this, then we're going to end up with sort of two cases. So case 1 is that d0 phi epsilon is less than x, sorry, minus this is less than or equal to 0. or 0 is less than x is less than d0 epsilon. Okay, and so, well, this we already know is going to tell us that a to the x, mod of a to the x is less than epsilon. We already know that. Minus 1. Whoops. This is going to tell us that 0 is less than or equal to x is less than minus x is less than d0 phi epsilon. And so then that means that mod a to the minus x minus 1 is less than phi epsilon. And so that means that mod of ax minus 1 is less than epsilon. And so that's our continuity at 0 from sort of both sides. And then that sort of extends to being fa, sort of restricted to the rational numbers, is continuous everywhere in the rational numbers. Okay, because we sort of can use the multiplicative rules of exponentiation to sort of drag our continuity around. So in particular, if we take, let's see, mod of x minus y minus x is less than delta 0 a to the minus x epsilon, then that is going to sort of tell us that mod of y minus x is less than delta 0 a to the minus x epsilon. We've already said that, which we can then sort of use our continuity thing at 0 and say, well, this means that a to the y minus x minus 1 is going to be less than a to the minus x epsilon. We then multiply up by a to the minus x, and we're going to get a to the y minus a to the x less than epsilon, so we've got sort of continuity everywhere. And then we sort of use this fact that the rational numbers are dense in the real numbers. And so sort of a non-technical way of explaining this statement is that every real number is infinitely close to infinitely many rational numbers, right? You can sort of always choose any distance about any point in the real numbers, and any sort of interval around that point will contain an infinite number of rational numbers. And so that sort of means that we can sort of uniquely extend to any rational function that is continuous to a continuous function on R. So unique continuous extension to R. Okay, where if we sort of take qi, sort of some sequence, I goes from 1 to infinity, a subsequence of q such that the limit of, as I goes to infinity, of qi is equal to some x in the real numbers. Okay, so we take any rational series or rational sequence that approximates this arbitrary real number x, then the limit as I tends to infinity of fa of qi is a good sort of well-defined and continuous and satisfies all of our properties definition of fa of x. Okay, and in particular, if we sort of have that x is the limit as n goes to infinity of some I goes from 1 to n of qi. So for example, pi is equal to 3 plus 1 over 10 plus 4 over 100 plus 1 over 1,000 plus, and so on and so on. If we have this, then a to the x we can say is going to end up being, sort of using our sum and product rule, a to the x is the product from I equals 1 to infinity of a to the qi. Okay, so we now have a to the x defined for any real number. And we can also say that if a is not equal to 1, a to the x from r to real numbers greater than 0 is invertible. Okay, And how can we sort of say that? Well, again, we're going to take, first of all, a greater than 1. And we'll sort of say, well, a to the x is 1 to 1. It's injective because if x is greater than y, then a to the x minus y is greater than 1. So a to the x is greater than a to the y. Okay, so they're not equal, so it's injective. And then we can sort of say that it's also surjective because we use the intermediate value theorem. So basically that says that if fa covers all values between 0 less than x less than infinity, then, or sort of, what do we mean? Well, we mean that the sort of lowest, the greatest lower bound of the values fa of x, you sort of can say that it's greater than 0, but you can't say that it's greater than anything greater than 0, right? You can't say fa of x is always greater than 0.1 because you can always just move x down by 1 and divide by a and go down, sort of thing, and less than infinity. And so basically, so there always exists x such that fa of x equals y, where y is sort of in this open interval from 0 to infinity, where we're sort of not including 0 and infinity. And so a to the x is invertible, and we call that inverse log a of x, and a to the log a of x is equal to x. This is sort of our thing. Okay, so now let's actually differentiate. So step 2, differentiation. We've now sort of actually done most of the hard work. Lots of what we do now is just kind of repeating results we've already used. So first of all, let's define ga of x to be a to the x minus 1 over x, where x is not equal to 0. Okay, we're not going to define it at 0 yet. Then the derivative of a to the x is the limit as h goes to 0 of a to the x plus h minus a to the x over h, which we can then take out this factor of a to the x. So we get a to the x, the limit as h goes to 0 of a to the h minus 1 over h. You'll notice that this is the limit of GAH to 0. And so this is a to the x times the limit h to 0 of GA of h. Now, what's interesting about this? Well, this thing doesn't depend on x, right? This is just some constant. If it exists, we sort of haven't proved that it exists yet. But if it exists, it's just some number ka. And so that means that a to the x has this great property where its derivative is proportional to itself. And that's sort of why we care about e to the x in the first place, right? Because its derivative is itself. And so what we're going to do is we're going to prove that, first of all, ka exists whenever a is greater than 0. And then we're going to show that actually there's a special number where ka is equal to 1. But first, we're going to have to sort of show that ka exists, which is a bit awkward, but it's not too bad now. So we know that g is sort of continuous outside of x is 0, right? Because this is just sort of a normal function. A to the x, we've said, is continuous. Subtracting 1, that's fine. Dividing by x, that's fine for x not equal to 0. So let's do a little bit of algebraic manipulation. First of all, we can look at g of 1 over a, x. So limit as x goes to 0, g 1 over a, x. This is the limit. X goes to 0 of a to the minus x minus 1 over x, which is going to be minus the limit x goes to 0 of 1, sorry, no minus, 1 minus a to the minus x over minus x, but then these minuses are the same, so then this is minus the limit x goes to 0 of a to the x minus 1 over x, right? You just replace x with minus x and pull out that minus. And sort of basic algebra, I'm not going to go through it here, but GA of x minus GA of minus x is x GA of x GA of minus x, and GA of minus x is GA of x over A of x. So we can sort of sub those things together, and GA x minus GA minus x is x a to the minus x GA of x squared. And we can sort of also notice that if x is not 0, then GA of x is actually positive, because either sort of x is greater than 0, then a to the x is greater than 1. We're sort of fixing a greater than 1 here. And so both sides are positive, or x is less than 0, a to the x is less than 1, and so both numerator and denominator are negative. So we get that. Now, because it's sort of continuous everywhere apart from 0, there are sort of a few things that can happen. One thing that could happen is that sort of no limit exists anywhere. Sort of like this graph here, this is minus 1 over x, so it's continuous everywhere apart from 0, but it's unbounded. So we don't end up with a sort of proper limit at 0. So we don't want that. Another case is sort of it's continuous and it's bounded, but here it goes to here, and here it's going to tend to here. Again, this is not sort of continuous at 0, it's not defined at 0, because the limits are in different places. So what we need to do is prove that the limit x goes to 0 from above of GA of x is equal to the limit x goes to 0 from below of GA of x, and that neither of these things are infinite, right? We need these to be finite numbers. We don't want it sort of both shooting up off to infinity. We want something like it tends towards a number and it tends towards a number. And that's what we're going to sort of find. So we sort of already know that if 0 is less than x is less than 1, then a to the x minus 1 is less than x times a minus 1, right? This was what we did before, but with p and q instead of x. And so that means that 0 is less than GA of x is less than a here, because we sort of cancel the x on the top and bottom, we subtract off the 1s and whatever, we get this. A minus 1. Yep. Okay. And also 0 is going to be less than a to the minus x is going to be less than 1. And so that means that 0 is less than x a to the minus x GA x squared is less than x a minus 1 squared. Okay. So this is remember, this is our difference, GA of x minus GA of minus x. Now, that tells us that this thing here must have a limit, because we use this thing called the squeeze theorem, where we've got sort of one function which is quite boring, it's just sort of 0. And we've got another function which is a straight line, it's x times a minus 1 squared. This is 0. Well, our sort of interesting function, our sort of, let's call this HA of x, let's say, is sort of stuck between these two lines. It can't escape, and so it's driven to meet at 0 where these two things meet. And so that means that the sort of limit as x goes to 0 of GA of x minus GA of minus x, this is from above, is equal to 0. And so that tells us that our sort of two functions are going to approach each other. So we now have sort of two cases. Either these two things sort of suckered into each other and they're forced to approach each other, and we get something like this, or we get something where they sort of go to being equal but infinite. So we need to sort of prove that that's finite, but that's actually fine, because we know that GA is bounded, because we already said that GA of x is less than a minus 1 in this region, so it can't run off to infinity, and continuous, and so therefore Ka equals the limit of x goes to 0 of a to the x minus 1 over x exists for a greater than 1, and we can sort of remember that we then worked out k of 1 over a was minus that, so we actually get any k. So any k greater than 0, because k of 1 is the limit as x goes to 0 of, well, 1 to the x is 1 minus 1 over x, and this is 0 because it's just the limit of 0. Okay, so now we're going to look at some properties of Ka. So we've already sort of shown that Ka is minus K1 over A, and K1 is 0. Now we can sort of say as well K a to the x, right? This is the limit h goes to 0 of a to the x h minus 1 over h, which is x times the limit h goes to 0 of a xh minus 1 over xh. Well, now we can just say this is xh, it's x k a. So we've got this sort of multiplicative power law for k. And we can also sort of say, well, remember we showed that a to the x was invertible. So if b and c are greater than 0, a is some number greater than 0, then if we let log a of b equal x, log a of c equal to y, so a to the x is b, a to the y is c, then k of bc is k of a to the power of x plus y, right, from our sort of old property of exponentiation, which is then x plus y times ka, but xka we already know is kb plus kc, right, for the same reason, because a to the x equals b, that means that kb equals xka, and kc is yka. So k has this property where when you multiply two arguments together, you add the results, which, I mean, has probably sort of spoiled it for a few people about what k is, but, I mean, we already knew what the derivative of e to the x was as well, so this whole video is sort of, you go into it knowing the ending. Okay, so then we need to prove that k, which is this function that sort of takes a real number that's greater than 0 and it's going to give us some real number, we need to prove that this is continuous. And we do that sort of in the same way as we did it before. We sort of started by not at 0 this time. We show that it's continuous at 1 from above. Okay, and we can do that because, well, we already know from sort of looking at it before that we had our bound on Ka between 0 and 1 was 1 plus a. So we already know that Ka is less than or equal to a minus 1 from before, just from sort of the bound on Ga of x. So if Ka is less than or equal to this, then we can just sort of say if 0 is less than or equal to, sorry, not 0, 1 is less than or equal to a is less than, let's say, 1 plus epsilon over 2, then 0 is going to be less than, Ka is going to be less than epsilon, or less than or equal to epsilon over 2, which is less than epsilon, right? So continuous at 1 from above, Then we do what we did before using that phi that told us about the continuity of 1 over x. So if a minus 1 is less than the minimum of, so we'll call this thing equal to d epsilon. So minimum of d epsilon and phi. D epsilon, the phi and the d have sort of changed places because 1 and 0 have changed places and things like that here. So we get this. Then we get sort of two cases. So either 1 is less than or equal to a is less than 1 plus d epsilon, in which case we already know that mod ka is going to be less than epsilon, or 1 minus phi d epsilon less than a less than 1, which tells us that 1 over a is going to have sort of 1 less than 1 over a less than d epsilon, which tells us that mod k 1 over a, which is mod of ka, because they're sort of just related by a minus sign, is less than epsilon. So k is continuous at 1. And then we can sort of continue and say, well, k is continuous for any a greater than 0. And we can sort of do that using, if we call this minimum here, we'll call this delta epsilon 0, so epsilon and at 0. So we sort of say, well, if b minus a is less than a delta epsilon 0, then b over a minus 1 is going to be less than delta epsilon 0. And then k of b over a, the mod of this, which is the mod of kb minus ka, is less than epsilon. Okay, and so this thing, delta epsilon a, tells us that we can sort of always make k continuous everywhere. So we're nearly there. The problem is that just because it exists in continuous doesn't mean that it sort of has this nice property of somewhere it will equal 1. The only value we know right now is that it's going to equal 0 at 1, but it could equal 0 everywhere. So we sort of need to work it out. And so what we're going to do is we're going to sort of calculate k a for b equals 1 minus a, somewhere between 0 and 1. So let's sort of work out, we sort of know that the derivative of x to the p over q is p over q x to the p over q minus 1, right, for p over q, a rational number. We're going to pretend that we don't know the derivative for a real power because that kind of actually relies on differentiating e to the x. So we won't do that yet. Now, we've got this derivative, and that sort of tells us what 1 plus b to the 1 over n is, because we can sort of Taylor expand this. We know that this is going to be sort of 1 plus 1 over n b plus 1 half 1 over n 1 over 1 over n minus 1 b squared plus, and so on, right? And so therefore we can work out GA at 1 over n is equal to n times 1 plus b to the 1 over n minus 1, right? This is just the definition of GA, which is, we'll do all of it, so n, and then we sort of express this sum, this expansion, so it's the sum from r equals 0 to infinity, our sort of power expansion, times b to the r. This is sort of all together minus 1, and then we sort of look in this and we work out the coefficients here. Well, it's the product from I goes from 0 to r minus 1, right? We have r minus 1 terms in our sum, in our product, sorry. So 0 terms here, 1 term, 2 terms, and it's 1 over I plus 1 times 1 over n minus I. And you can sort of then expand this out, work it out, and you're going to get that it's something like b plus 1 minus n over n b squared over 2 factorial plus 1 minus n 1 minus 2n over n squared b cubed over 3 factorial plus a lot of other things, or in sort of infinite form, this is going to be the sum from r is going to equal to 1 now. The 0 term is going to get cancelled out by the minus 1. So 0 to infinity, and then we get a product up here. I is going to go from 2 to r, 1 plus 1 minus I, n, b to the power of r over r factorial, and divided by n to the power of r minus 1. This product is sort of contained like this. So that's our next step. That's still sort of a bit funky, but GA is continuous. And so GA is continuous. So that sort of tells us that GA, or the limit as x tends to 0 of GA of x, is going to also be the limit as n tends to infinity of GA of 1 over n, because 1 over n is going to tend towards 0, and so therefore GA of these values is going to sort of tend towards the limit. And we can work out this limit from GA. So first of all, the limit as n goes to infinity of these sort of weird terms, the product from I equals 2 to r, 1 plus 1 minus I n over n to the r minus 1, where we've got sort of the brackets on top, the sort of constant terms, this plus 1, this is sort of going to be irrelevant. All we're going to care about is these 1 minus i's. And then the sort of the powers of n, we're going to get an n to the r minus 1 on top, n to the r minus 1 on the bottom. Those are going to cancel out. And so this is going to end up being, you can sort of work it out, 1 minus 1 to the r minus 1, r minus 1 factorial. And so then we plug that back into our sort of formula for GA 1 over n, and we find that the limit n goes to infinity, GA 1 over n will be sum r from 1 to infinity minus 1 to the r plus 1 br over r. You may recognize this. And so we can then also plug in the specific value. A is 3 over 2, or B is a half. And what we're going to do is we're going to sort of pair up these terms. So we're going to pair the 1 term with the 2 term, and so on. And this is Ka, obviously. So K3 over 2 is the sum from r equals 1 to infinity of the sort of first term, which is 1 over 2r minus 1, 2 to the 2r minus 1, minus 1 over 2r, 2 to the 2r, okay, or the sum from r equals 1 to infinity of 1 over 2 to the 2r times 2r plus 1 over 2r minus 1. Okay. And so we've got that it's an infinite sum, and each of the terms in the sum is greater than 0, and so therefore K3 over 2 is greater than 0. That's sort of all that we really need, because then it tells us that if A is greater than 0, then K2A over 3 is going to be Ka minus K3 over 2, and K3A over 2 is Ka plus K3 over 2. And so we can sort of make our K as big or as well, as largely positive infinite or as largely negatively infinite as we want by just multiplying by the 3/2 or 2/3, right? We're going to sort of get arbitrarily far away from zero by doing that, because we sort of keep adding on k3/2, or we keep subtracting off k3/2. And so therefore k is unbounded. And it's continuous. So that means that sort of k as a function from the positive numbers to the real numbers is invertible. We won't necessarily say invertible. We won't prove it because we don't need to prove it. Or we will, but in a different way. But importantly, we use this intermediate value theorem again, which says that, well, it starts at negative infinity, it ends at positive infinity, it's continuous, and so therefore, you can always solve for ka equals to x, right? There's always a solution, possibly multiple. And so in particular, there's going to exist some number e in the real numbers such that ke is equal to 1. Okay? And this is e. So ke equals 1, or the derivative of e to the x is e to the x. Or we could form a Maclaurin series from this. E to the x is equal to the sum from r equals 0 to infinity of x to the r over r factorial. And then this you can actually also see as the limit as n goes to infinity of 1 plus x over n to the power of n. These are sort of both valid. And we can also say that e, well, that's e to the power of 1, so that's going to be the sum from r equals 0 to infinity of 1 to the power of r is 1 over r factorial. So 1 plus a half plus a sixth plus a 24th plus a 120th plus. And so that's where we get this number 2.71828182845 and then it keeps going. And so that's how you differentiate e to the x. And let's also just quickly sort of show this off. We define ln of a to just be the log to the base e of a, so that a to the x is e to the ln a times x. And so if we differentiate this first side using sort of our rule, we know that this is going to differentiate to ka a to the x, whereas this is going to differentiate using the train rule to ln a times e to the ln a times x, which is a to the x. We cancel those, and so ka is log a, which you probably would have guessed from sort of the expansion we had for ka was just the Maclaurin expansion for log of 1 plus b. All of its sort of properties are the properties of logs. And you can also, if you sort of already know the derivative of a to the x, you can evaluate using L'Hopital's rule, right? So the limit as x goes to 0 of a to the x minus 1 over x. If you already know how to differentiate these things, then differentiate the top, we get log a times a to the x. On the bottom, we get 1. So the limit, again, as x goes to 0, which is ln a. So that's how you differentiate e to the x sort of properly in quite a sort of difficult and mathematically semi-rigorous manner. I'm going to put a link to my website where a copy of the sort of notes I read out from on this video will be. So maybe you want to sort of read through those and go over it yourself. I've got loads of other stuff on there. Yeah, I will see you in my next maths adventure. Bye.